Hello and welcome back. In this video lesson, we're going to look at eigenvalue dominance and decomposition. So one of the things we've already described or seen that if you repeatedly multiply some vector by a matrix A over and over again, it performs a geometric transformation. It rotates and scales that vector. But one of the things we noticed in the last lesson is that repeated multiplications by A cause that vector to rotate in the direction of the eigenvector whose eigenvalue is the largest in magnitude. So we're going to provide some justification for why that happens. So for an n by n matrix A, we know we're going to have n eigenvalues, lambda 1 through lambda n. And we're now going to label them in descending order of magnitude. So notice that we have absolute value signs. So for example, if we had an eigenvalue of -10, let's say, then we would say that -10 is the dominant eigenvalue provided that all the other ones were smaller in magnitude. So this could be like a 3, and technically 3 is larger than -10, but if you take the absolute value and you just look at the magnitude, -10 has a magnitude of 10, 3 only has a magnitude of 3. So we're going to just label them with this convention in descending order to make them easier to organize. This isn't a hard and fast rule, it's just something that we tend to do. That way we can always say lambda 1 is the largest magnitude eigenvalue. So the eigenvalue with the largest magnitude, the largest absolute value, is called the dominant eigenvalue. And we're going to make the following claim. When we multiply some vector repeatedly by a square matrix A, that is a to the t power times x naught, then as t approaches infinity, that is as t we make that power really, really large, the resulting vector, which we'll refer to here as the output of that, we'll call that b for the moment, b equals a to the t times x naught, rotates/stretches in the direction of the eigenvector corresponding to the dominant eigenvalue. That is, if v1 represents the eigenvector of the dominant eigenvalue, then we can say that as t approaches infinity, the limit of that multiplication results in something that approaches v1. And let's now provide some additional justification for that. But furthermore, as this vector continues to get multiplied by A, that is stretch rotated, after t becomes really large, the initial vector gets closer to the eigenvector, so the eigenequation AV equals lambda v takes effect. So imagine that this vector x naught, that after repeated multiplications points in the direction of the eigenvector, now additional multiplications by A cause that multiplication to produce a scalar multiple of that eigenvector. And so the only remaining alteration that will take place on this final vector v is the scaling effect of lambda. If lambda equals 1 is the dominant eigenvalue, then the resulting vector will reach a steady state and will not change. So here is an example. The matrix A equals 3, 0, -1, 2 is the transformation matrix for some initial vector x naught equals xy. We demonstrate that this vector will rotate in the direction of the eigenvector corresponding to the dominant eigenvalue, and once there, will only become scaled by the dominant eigenvalue for all further multiplications by A. So here are the outputs, and we're going to use our applet from our last lesson to show this. Lambda 1 is equal to 3 is the dominant eigenvalue, and so this one is dominant. And this means that eventually, once we multiply our initial vector by A enough times, that vector is going to rotate in the direction of 1, 0. So what we're saying essentially is that it doesn't matter what eigenvector or what vector you start with, provided that it's not already an eigenvector, but that progressive multiplications by A will cause this vector to rotate. So if this is my x naught, then multiplication by A, maybe one time, will rotate and stretch it a little bit, but ultimately this vector will rotate in the direction of the dominant eigenvalue, which is in the direction of 1, 0. So what we're saying is that if we take A to a large enough power and multiply it by x naught, what we will get approximately is lambda 1 times v1, or some multiple of lambda 1. So I should probably say some multiple of lambda 1. So that is, eventually it will rotate enough and stretch enough to become rotated in the direction of 1, 0, and then it will just continue to stretch in that direction. So let's go ahead and take a look at the applet that's going to demonstrate how this works. So here we have the applet pulled up, and what I have entered in here is the initial matrix 3, negative 1, 0, 2, and I'm just going to start off with this arbitrary vector 2, 1, which you can see is both the red and black vector. The red vector will stay there as a reference, or the black vector will stay there as a reference so we can see what happens. So when I multiply by a one time, so this is a to the first times the 2, 1 vector, basically one multiplication by a will cause this 2, 1 vector to rotate a little bit, and notice that it's become scaled as well. If I do it again, and let me just show these two things here. Ratio of y to x and a to the first times x. So the y value that we would get is 2, the x value is 5. You can see that that vector is 5, 2. So the ratio of 2 to 5 is 0.4. And the multiplier, so a to the first times x gives me 5, 2. And then if I do it one more time, if I drag the slider to t equals 2, I'll get the vector 13 to 4. 13 and 4, which is this vector that I would get if I push this over one more time. And you can see what's happening here now. A squared times the initial vector produces 13 and 4 as its components. That's the components of this red vector, with the ratio of y to x of 4 to 13, which is 0.31. If I continue to do this, watch what happens to that vector. It's progressively rotating in the direction of the dominant eigenvector with the largest eigenvalue. So you can see at this point that a to the 17th times that initial vector produces this ugly vector here, 1, 2, 9, 2, 7, 1, 2, 3, 5, as the x component, 1, 3, 1, 0, 7, 2 as the y component. Now that may not seem like a 1 to 0 relationship there, but you can see that if I divide the y component by the x component, the rise to run of that vector is pretty much 0. So we can see that this is essentially a relationship of 1 to 0. Not exactly, but you can see that this top number is much, much larger than this bottom one. And you can see that what happens eventually is that vector becomes even closer to 0. And what we should see is that the additional multiplications cause this vector to become larger by a factor of 3. So to kind of summarize that picture, here's the one that we started off with. This was when we had a to the 0 times the 2, 1 vector, which a to the 0 times the 2, 1 vector is just the 2, 1 vector. But then eventually when we make the power large enough, we can see that that vector, that red vector, is pretty much in the direction of 1, 0. And if I multiplied it again by a repeatedly, I would see that basically this vector just gets tripled because now it is in the direction of the dominant eigenvector. And let's just show that it didn't really matter that we picked 2, 1. We could have picked something else and it still would have happened. So let's show if we, for example, pick the vector negative 0.5 and positive 2. Okay, there's our initial vector. Oops. So watch what happens. Right now, our vector points in the direction of negative 0.5, 2. And if I multiply it by a one time, you can see that that red vector kind of rotated to the left, but as I continue multiplying it repeatedly, it again, notice, points in the direction. Now 1, 0 is to the right, but still, even this vector right here, negative 87, blah, 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 and the y component being that, that's pretty much a multiple of the 1, 0 vector. Once again, it's just a negative multiple of the 1, 0 vector. And we see that it still points along the x-axis. Negative 1, 0, remember, is also an eigenvector. If 1, 0 is an eigenvector, that just means that the y component has to be 0 for it to be considered an eigenvector. We can see again that thing rotates in the direction of the dominant eigenvector with a scalar multiplier of about, right now it's about 2, but that's only because my power is not large enough. If I made this slider go up to 100, we would see that the relationship between like a to the 100th times x naught and a to the 101st times x naught is there would be a multiplier of 3 there. So let's go ahead and explore mathematically why this happens. And before we get into the diagonalization theorem, I also want to have us recall that we also know that if you want to take a to the t power, you could use the diagonalization and write it as x times d to the t times x inverse, as long as the eigenvectors are linearly independent, where, remember, the X matrix just contains the eigenvectors of A as its columns, now written in order of descending magnitude of the lambda. So we've said that we're going to call lambda 1 be the dominant eigenvalue, so we'll list V1 through Vn, which corresponds to the D matrix, which will have along its diagonals lambda 1 through lambda n, and then zeros everywhere else. So for example, if we wanted to do this for t equals 17, a to the 17th times the 2, 1 vector should give me the same answer as taking x, the matrix with the eigenvectors. So the eigenvectors are 1, 0, and 1, 1. 1, 0 is the eigenvector corresponding to the eigenvalue of 3. 1, 1 is the eigenvector of the eigenvalue 2. So notice that we've listed the largest magnitude eigenvalue, followed by the next largest in magnitude, and then we list their the eigenvector of 3 first and then the eigenvector of 2 second, multiplied by the inverse of that eigenvector matrix. So this is really right here, this is just a to the 17th written in terms of the decomposition, multiplied by the 2, 1 vector gives us exactly the same result that we saw in that applet. We see also here, the thing to note intuitively is 3 to the 17th. This is going to be much larger than 2 to the 17th. We're multiplying by 3 17 times, and we're multiplying by 2 17 times. So these two numbers there'll be a big discrepancy between them. Now, if this was 3 to the 100th, that would be so much larger than 2 to the 100th. This means that whatever components in this multiplication get multiplied by 3 to the 17th will be of much more significance than what components get multiplied by 2 to the 17th, which further justifies our claim that 3 is going to be the dominant eigenvalue. Now, if you carry out this multiplication here, and you take 3 to the 17th times the 1, 0 vector, 0 times the 1, 1 vector, you'll have 3 to the 17th times 1, 0, and then 0 times 1, 0, plus 2 to the 17th times 1, 1, will give you 3 to the 17th times V1, plus 2 to the 17th times V2, which, as the power here gets really large, 2 to the 17th times 1, 1 will appear much smaller than 3 to the 17th times 1, 0. But we can further make this relationship clear by looking at the diagonalization vector decomposition theorem. And this is going to be the same idea, but written in vector form. The theorem says that the dominant eigenvalue is the long-run transition factor, the scalar, and the corresponding eigenvector shows the relative ratio of long-run values. What I mean by that is, as this power became large, we noticed that the ratio between the x and the y components is the same as the ratio between the x and the y components of the dominant eigenvector. So the dominant eigenvector corresponding to the dominant eigenvalue is 1, 0, and we see that the relationship between this really large number here at the top and this number here down at the bottom, that's pretty much a 1 to 0 ratio, or a 0 to 1 ratio if you want to do y to x. More precisely, we can write the state vector at time t in the following form. So x of t, this is the old form where we basically take a to the t times the initial state. And we're going to argue that you can actually write x sub t in this vector equation form, k1, lambda 1 to the t v1, plus k2 lambda 2 to the t v2 plus etc. depending on how big your matrix is. Remember, these are n by n, so you're going to have n terms in this equation. If a was a 2 by 2, we would only have 2 terms. If a was a 3 by 3, we'd have 3 terms. And then k1 and k1 through kn are just some constants. That is, this says that xt, the vector that's been multiplied by at times, can be written as a linear combination of the linearly independent eigenvectors along with their eigenvalues. So each one of these terms, notice, represents one term in the whole expression, and each one of these terms involves an eigenvalue and the corresponding eigenvector. Same thing here, eigenvalue, corresponding eigenvector. The assumed condition for diagonalization was that the eigenvectors are n linearly independent eigenvectors in Rn. So if this is the case, we know that if you have a bunch of linearly independent eigenvectors, in fact, as many as you do corresponding to the size of the dimension that you're in, so if you had 2 linearly independent vectors in 2 dimensions, you could span all of R2, meaning you could get to any location in Rn by putting scaled versions of these vectors tip to tail. So that's the geometric interpretation. So think back to the hoverboard and magic carpet problem. So if that's the case, if v1 through vn are linearly independent, that means I could write any vector as a linear combination of them. So my x0 vector is a special vector, and I can write that as a linear combination of my eigenvectors. So k1, k2 up to kn are just some constants. Now, we know that if we multiply x0 by a, that's going to produce the state vector at time 1. Well, what's x0 equal to? Well, we just said that you can write x0 in terms of the eigenvectors as a linear combination of them, provided they're linearly independent. So all I've done here is replaced x0 with what x0 is equal to, which is k1 v1 plus ... So now when I multiply x0 by a, I'm going to distribute a. Since k1 is a constant, by our properties of matrix algebra, a can pass the k1, a can pass the k2. It just has to stay on the left side of the vector. So we'll have a v1, a v2, a vn. And the beauty of this is that when we multiply a by eigenvector 1, that's going to be lambda 1 times v1, because that's what the eigenequation says. A times v2 is lambda 2 v2. A times vn is lambda n vn. Now, if we do this with a second multiplication, if we wanted the state at time 2, that would be a squared times the initial state. A squared times the initial state is the same thing as a times x0. And by the associative property, I can multiply a times x0 first. Well, hey, from up here, I already know that a times x0 is equal to this expression. So there's just me putting that expression in for a times x0. And again, I'll distribute the a. k1 and lambda 1 are constants, so the a can go squeeze between the lambda 1 v1. So there it is. And distribute that to the next term, a v2, all the way to the last term, avn. Well, av1 is still lambda 1 v1, av2 is still lambda 2 v2, and avn is still lambda n vn. So that means I could make that replacement in there. And if I look at this, I have k1 lambda 1 v1. Well, lambda 1 times lambda 1 is a scalar times a scalar, which is lambda 1 squared. Lambda 2 is lambda 2 squared. Lambda n times lambda n is lambda n squared. And you can probably see that whatever t is here, that ends up being my exponent on the lambda. So following the pattern, we can confirm that in general, if I wanted the state vector at time t, which is a to the t times x0, that would be the same thing as taking k1 lambda 1 to the t v1 plus k2 lambda 2 t to the t v2, and so on. Okay, so now we've basically just proven this theorem. We've allowed ourselves to justify this by using kind of this math principle of linear independence. And this is why we talk about it, because it helps us do things like this, see things in a different way. So now that we have this vector equation for how to predict the state at time t in terms of the lambdas, now we can argue that the lambda that's being raised, the largest magnitude lambda that's being raised to the t power, is going to cause that particular term to be a lot larger than any of the other terms for big enough values of t. So lambda 1 is the biggest magnitude eigenvalue, and if you raise a really large number to a really large power, that's going to be significantly larger than any of these other terms, which justifies why this vector starts to rotate in the direction of v1, and every time you increase t by 1, we get one more multiplication by lambda, and there's that scalar effect that we're describing. So these k1 through kn's can be found by satisfying that condition, because we just said that k1 through kn are just the scale factors that we have to put on the vectors before we put them together tip to tail to reach the location of where x0's tip is located. These just help us express our initial state vector as a function of the n linearly independent eigenvectors. So let's do an example with this to see how this all works. Consider again a equals 3, negative 1, 0, 2 with initial state vector x0 equals 2, 1. Using the diagonalization vector decomposition theorem, find k1 and k2 and provide support for why it makes sense that this vector will get transformed in the direction of v1 equals 1, 0 with scalar multiplier lambda 1 equals 3. And we should have said in here, after many multiplications by a. Okay, so here's what we're going to do. We are going to, first of all, find out what our eigenvectors are, which we said that we found using Wolfram alpha that lambda 1 was 3, and lambda 2 is 2. Lambda 1 equals 3 corresponds to v1 equals the 1, 0 vector, and the v2 is the vector 1, 1. So using the diagonalization decomposition theorem, where that vector will be after t multiplications by a is going to be given by k1 lambda 1 to the t times v1 plus k2 lambda 2 to the t times v2. And we only have two eigenvectors and two eigenvalues, so this will only have two terms in it. What we need to do first is we need to solve for k1 and k2 before we apply this formula. And the way we're going to do that is our x0 vector, we know, is going to be some linear combination of our two eigenvectors. And now as we do that and plug in our numbers, we know that x0 is the initial state vector that we're given in this problem, which is 2, 1. k1 times v1, v1 is the vector 1, 0, plus k2 v2, which is the vector 1, 1. Now I have a system of equations to solve for k1 and k2. So if I set up my Gaussian matrix, 1, 0, 1, 1, 2, 1, which recall these are my coefficients for k1 and k2, and I perform Gaussian elimination on this, I will end up with the vector, let's see here, this will give me 1, 0, 1 and 0, 1, 1. So interpreting that, that says that k1 equals 1 and k2 equals 1. Let's check our work. So as a check, we just want to verify that if I take 1, so that's k1 times v1, which is 1, 0, plus k2 times v2, that in fact I do get the initial state vector. Now you can see that these are linearly independent because 1, 0 and 1, 1 are not scalar multiples of each other. So this will produce 1 times 1, 0 plus 1 times 1, 1. That will give me my initial vector, my initial vector x naught, which is exactly what I sought out to solve. Now we're ready to express this in general terms. So here we now are going to write where that vector is. Whoops, don't know what happened here. Sorry about that. And so let's see. So now we're going to plug in what values we have here. So remember, xt vector just contains the x component at time t and the y component at time t. And we just found k1 is 1. Lambda 1 is 3, so this is going to be times 3 to the t power, times v1, which is the vector 1, 0. k2 was found to be 1. Lambda 2 is 2, so we have 2 to the t power, times v2, which is the vector 1, 1. So as t approaches infinity, this term here is going to blow up, gets much larger than this term over here. So this is only 2 to the t power. So you can see that as t becomes really, really large, this term essentially becomes negligible. Now, I'm not saying that it goes away completely, but 2 to the t power, if you look at 2 to the 100th versus 3 to the 100th, the order of difference there is much larger. And so now what we want to be able to do is to write out the components. So just to see that even though this is a vector equation, this gives me a formula for x at time t is going to be 1 times 3 to the t times 1, which is just 3 to the t, plus 1 times 2 to the t times 1, which is just 2 to the t. And y sub t will equal 1 times 3 to the t times 0, which is just 0. 1 times 2 to the t times 1 is just 2 to the t. And so you could see that as t approaches infinity, this term we said becomes negligible. Essentially doesn't become 0, but comparatively to 3 to the t becomes 0. So x sub t is going to get infinitely large. So we can say that as t approaches infinity, x sub t becomes essentially 3 to the t, and y sub t becomes essentially, comparatively, it becomes 0. I know that 2 to the t continues to get larger and larger, but the relationship between those becomes 3 to the t and 0. So you can see here that if I increase t by 1 more unit, this vector is just going to get scaled in the direction of the 1, 0 vector by a factor of 3. So it'll get 3 times larger when I continue multiplying it by another multiplier of a. So how big t needs to be in order for it to start to point in that direction is not entirely obvious. It really depends on how close these two eigenvalues are to each other in magnitude. In this case, it may take many more multiplications by t for that vector to really become a vector that points in the direction of 1, 0. So let's just go ahead and provide a little bit more support for this. We'll say that if we wanted to check our work and just to see that x sub 17 and y sub 17, remember this is just our state vector at time 17. So this is x sub 17. And we're just going to show that you can use these two formulas now to compute them. So x sub 17 is going to be 3 to the 17th plus 2 to the 17th. And y sub 17 is going to be 2 to the 17th, which lo and behold comes out exactly to what we achieved earlier. 235. And this component down here becomes 131072. So that's just a way for us to check that this set of formulas here does the same thing for us. But what we can do now is we can actually graph xt and yt on Desmos, and we can see what happens to both of those components as t becomes increasingly large. So let's go ahead and take a look at that briefly. So here I just have x sub t of x equals 3 to the x plus 2 to the x. We can't use t in here, unfortunately, so this x here is actually the x component of our vector. This x here actually represents time. And y sub t of x equals 2 to the x. So the one thing you can see here is the blue curve represents what's happening to my x component as a function of time, which is my horizontal axis. And you can see that these two curves are getting increasingly farther and farther apart. In fact, if I make just the y scale larger, you can see that those curves are the vertical distance between the blue curve and the green curve at x equals, say, 4. You can see that those two curves are 97 minus 16 units apart. But for x equals 6, you can see that those two curves are much farther apart, which means the ratio of the green curve, which represents the y value, divided by the x component, that relationship approaches 0. And one other thing I can do here is I can show a table of values. So here I'll just create a table, and I will call this, I'll look at different values of x. And here what I want to look at is x sub t of x1. And here I want to look at y sub t of x1. And now I just look at different values of x. So when time is 0, this just reproduces our initial state. Our x value was 2, our y value was 1. And that makes sense. Now when x becomes 1, so that's 1 multiplication by a, my x component becomes 5, my y component becomes 2. Over here what I'll do is I'll look at the ratio of y sub t of x1 divided by x sub t of x1. And you can see what's happening here. 1 to 2 is a 1/2 ratio, 2 to 5 is a 0.4 ratio, and if I continue doing this, let's say I make time 10, you can see how much faster that x component is growing. These two curves are farther apart. If I do it for time 100, you can see that this one's on the order of 10 to the 30th, but the x component is on the order of 10 to the 47th. And the ratio between those, you can see, is 2.46 times 10 to the negative 18th, which is effectively 0. Now, after 1,000 time units, x of t becomes so large relative to the y component that ratio of the y to the x is essentially 0, what that tells me is that the vector is now pretty much pointing along the horizontal axis. So our conclusion is we see that as t approaches infinity, again, just making the exponent larger and larger, the first term, 3 to the t times 1, 0, which is this term here, that term will be much larger than 2 to the t times 1, 1. And therefore, for very large t, x sub t is approximately going to be equal to 3 to the t times 1, 0. So you can see here that basically it's going to be some multiple of the 1, 0 vector. In our case, that multiple is not, again, quite 1 to 0, but it pretty much is a 1 to 0 relationship. And if I multiply by, let's say, multiply this thing by 3 again, the vector will point in the direction of 1, 0, and every 1 unit increase in t beyond that value will simply cause the vector to be scaled by 1 additional factor of 3. So it's going to point in the direction of 1, 0, but it's going to continue to get longer and longer and longer and longer. Let's take a look at our example from the human migration patterns in Flagstaff or in Coconino County. Remember that we had 5% of people in the urban environment at time n transition to the rural environment at time n plus 1. 85% of the people in the rural environment at time n stayed in the rural environment at time n plus 1, and 15% of the rural people at time n became urban people at time n plus 1, and 95% of the urban people at time n became urban at time n plus 1, or remained urban. So 95% of the people stayed. And then we were able to write it like this as the direct equation, where we just took a to the t times our initial state. And what we want to do here is to show, we already showed mathematically by computing the steady state vector what happens in the long run, but now we want to see, using the diagonalization vector decomposition theorem, we're going to write equations for r sub t and u sub t as functions of time, then explain why it makes sense that after repeated multiplications by a, that is, years passing, the transformed vector approaches the steady state ru equals 2575. So first of all, we need to compute the eigenvectors and eigenvalues of that matrix. So here they are. And now what we're going to do is, again, start off by writing our initial state as some multiple of v1 plus some multiple of v2. So we're going to solve for k1 and k2. Now our x0 vector, that was our initial state in this problem, which, remember, we had 20 rural people and we had 80 urban people at time 0. So now we have k1 times v1, which is the 1/3 1 vector, plus k2 v2, which is the -1 1 vector. And now we need to solve for k1 and k2. So that means we have a system of equations. Coefficients of k1 are 1/3 and 1. Coefficients of v2 or k2 are -1 and 1. And then we want to achieve the constants 20 and 80. So again, our k1 column, our k2 column, and performing Gaussian elimination on this using technology, we would get, we would get 1, 0, 75, and 0, 1, 5. So this tells me that k1 is 75 and k2 is 5. And again, we're just going to check to make sure this works out, so we believe it. So that means that if I take k1, which is 75, times v1, which is 1/3 1, and I take k2, which is 5, times the -1 1 vector, and I add these together, 75 times 1/3 is 25, 75 times 1 is 75, plus 5 times -1 is -5, and 5 down here. And now when we add these together, we see that 25 minus 5 is 20, 75 plus 5 is 80. So we have effectively solved for k1 and k2. So next, just like in the previous problem, what we're going to do is we are going to decompose this into the diagonalization vector decomposition theorem. And that says that x sub t, the two states at time t, are going to be k1 lambda 1 to the t times v1. And since this is a 2x2 matrix, it's only going to have two terms. In our next lesson, we'll actually look at multiple states where we can, we'll have a third term in it. And that would be the same process, just larger matrices to deal with. And so now I'm just going to plug in what I know. So I know xt contains my two states, r at time t, and the number of people in the urban environment at time t. k1 is 75, lambda 1 is 1, so we have 1 to the t power. v1 is the 1/3 1 vector, plus k2, lambda 2 to the t. Now lambda 2 is 4/5, which we'll write as 0.8. 0.8 to the t power, times v2, and v2 is -1, 1. So already one of the things to notice is that as t approaches infinity, if you take a decimal to a really large power, this guy here is going to approach 0 as t approaches infinity. This doesn't always happen, it just is the case here that one of our eigenvalues is a fraction, and when you raise a fraction to a large enough power, it's going to approach 0 for large enough t's. So at that point, we're going to see that what we're left with is, well, 1 to the t is 1. You can exponentiate 1 to whatever power you want. 1 to the 100th is still 1 times 1 times 1 times 1, dot, dot, dot. So this will just be 75 times a third, which is 25, and 75 times 1, which is 75. So we see that we're going to end up getting, in the long run, the state 25, 75. But let's write this out in scalar form. So r sub t is equal to 75 1 to the t times 1/3. Again, 1 to the t is just equal to 1 for all t. And so we'll have 75 times the 1/3 vector, which is just 25. And so for u sub t down here, let me write this in vector form, 75 times 1 to the t times 1 is just 75. And then I'm going to add to that k2 times 0.8 to the t times -1. So my k2, I forgot to write it in here. Here, my k2 was actually 5. And so we'll have 5 times 0.8 to the t times -1, which is minus 5 times 0.8 to the t. And 5 times 0.8 to the t times 1 is just plus 5 times 0.8 to the t. So now you can see what's happening here. As you raise for large enough t, this term will decay to 0. This term will go to 0. This term will go to 0, again, as t approaches infinity, and all I'm going to be left with is the constants 25 and 75. So let's go ahead and actually model this in Desmos to see what this looks like. So I'm going to go ahead and just say this is r sub t at time x, we have to use x here unfortunately, equals 25 minus 5 times 0.8 to the x power, and u sub t of x is equal to 75 plus 5 times 0.8 to the x power. And let's just go ahead and zoom in on this on a scale. We'll just say we'll go from time 0 to time 20, and here we'll go from y equals 0 to y equals, we'll say 100. So here we go. So we can see that the number of rural people starts off at 20 at time 0. At time 0, u sub t starts off at 80, but we can see that over time, u sub t drops by a little bit, and it starts to stabilize out by about time 14 or 15. R sub t rises from 20 and then stabilizes out after about, again, time 14 or 15. And let me just put in a couple of asymptotes here. Y equals 25, you can see y equals 75, that these asymptotes are actually going to be the values at which the rural population size stabilizes at and where the U population stabilizes at. And the important thing here is that we described that as t becomes larger and larger, that it's the dominant lambda becomes the multiplier. So once that vector rotates into its direction, which it's going to go in the direction of this v1, but it's only going to be scaled by 1 each time. And since 1 is the dominant eigenvalue, that means that basically any additional multiplications by a are really just going to scale it by 1, and that's why we reach the steady state. So we can argue that if your dominant lambda is a 1, that you are going to reach steady state, and only under those conditions can you reach a steady state. If this was a 2, then ultimately our initial state vector would transform into the eigenvector, but then it would be scaled by a factor of 2 each time, so the values inside of here would actually double in the long run and not approach a steady state like we have here. So here, once again, we just have, this is our urban population at time t, this is our rural population at time t, and then one other thing we should just note here is that our axis, our horizontal axis is time over here, even though we're using x and in place of time, but unfortunately Decimals doesn't recognize working with t as a variable. And so we see that steady state is definitely achieved. So conclusion is that we see that as t approaches infinity, the first term, 75 times 1 to the t times 1/3 1, will be much larger than 5 times 0.8 to the t, negative 1, 1. And therefore, for very large t, x sub t is approximately 75 times 1 to the t times that v1 vector, which, because this is a 1 to the t power and that equals 1, these values just become 25 and 75. That is, the vector will point in the direction of 25, 75, and every 1 unit increase in t beyond that value will simply cause the vector to be scaled by 1 additional factor of 1, a steady state. So that's where we'll stop this lesson. In the next one, we'll start looking at some modeling and how we can predict what happens when there's not a steady state. And things get very interesting when you start dealing with stage matrices, where you can actually incorporate a birth-death cycle into that process. So more on that in the next lesson.